Hello everyone, welcome to this video on number systems in digital electronics, prepared by Dr. Bhargav. A digital system processes discrete binary signals, unlike continuous signals. It works with two levels, 0 for low or off, and 1 for high or on. Examples include computers, digital clocks, mobile phones, and embedded systems. Digital systems are used in many areas, such as communication, business transactions, traffic control, and spacecraft guidance. They are also integral to medical treatment, weather monitoring, the internet, and various commercial, industrial, and scientific enterprises. Number systems are the foundation of modern computation. The radix or base in a positional number system is the count of unique digits used. For a base R system, the symbols range from 0 to R-1. Digital systems use various radices to balance readability and hardware simplicity. A number is expressed with a power series in R, as shown here. When the number is expressed in positional notation, the decimal point is called the radix point. Here A represents the weight of the position. The common number systems include decimal, with a base of 10, used for human interface and arithmetic. Binary, with a base of 2, is used for logic levels. Octal, base 8, is used for compact binary representation in early computing. Finally, hexadecimal, base 16, is used for memory mapping and debugging. The decimal number system has a base of 10 and includes digits 0 through 9. This system is used in our daily life. The table illustrates how numbers are formed sequentially using these 10 digits. In any decimal number, the rightmost digit is the least significant digit, with the least position value. Conversely, the leftmost digit is the most significant digit, having the highest position value. For instance, in the number 59, the 9 is the least significant digit, and the 5 is the most significant digit. The octal number system has a base of 8 and includes digits from 0 to 7. The numbers formed using these 8 digits follow a sequence where each column's value increments upon reaching 7 in the previous column. For octal numbers, the rightmost digit is the least significant digit, and the leftmost digit is the most significant digit. For example, in the number 47, the 7 is the least significant digit, and the 4 is the most significant digit. The binary number system, or base 2, includes only two numbers, 0 and 1, called bits. Since the digits are limited to 0 and 1, numbers 2 through 9 are not used. The numbers formed with these bits are shown here, continuing with increasing place values. In binary numbers, the rightmost bit is the least significant bit, or LSB, with the lowest position value. The leftmost bit is the most significant bit, or MSB, with the highest position value. This is illustrated with the binary numbers 11 and 1011. Binary is the language of circuits. A bit is a single binary digit, 0 or 1. A nibble is a group of 4 bits. A byte is a group of 8 bits. In terms of voltage, 0 represents low, or 0 volts, and 1 represents high, typically 5 or 3.3 volts. The hexadecimal number system, or base 16, is a compact way to represent binary data. One hex digit represents exactly 4 bits. Letters A through F are used to represent values 10 through 15. This makes reading and communicating long binary strings easier for engineers. This table shows the progression of hexadecimal numbers, starting from 00 and including letters A through F to represent values 10 through 15, and so on. This table summarizes the decimal, binary, octal, and hexadecimal representations for the numbers 0 to 15, highlighting the correspondence between the bases. Now, let us move on to the topic of conversion between different number systems. Number conversion in digital electronics is essential to bridge the gap between human-readable data, decimal, and machine-level processing, binary, enabling efficient data representation, hardware communication, and system interoperability. To convert a decimal number to any other number system, the method involves successive division by the target base. The remainders are recorded from the bottom up. This is used for conversions to binary and hexadecimal systems as well. For binary, divide by 2, and for hexadecimal, divide by 16. For decimal to octal conversion, we use successive division by the target base, which is 8. We record the remainders from bottom to top. For example, converting 220 base 10 results in 334 base 8. To convert the fractional part of a decimal number to octal, we use successive multiplication of the fraction by the target base, 8. Take out the integer part and repeat until the fraction is 0, or repeats. The example shown here details the process. For decimal to binary conversion, we use successive division by the target base, 2. The remainders are recorded from the bottom up. Converting 220 base 10 to binary yields 110, 11100 base 2. For the fractional part conversion from decimal to binary, we use successive multiplication by the base, 2, extracting the integer part each time. The example illustrates converting 0.625 base 10 to 0.101 base 2. For decimal to hexadecimal conversion, use successive division by the target base, 16. Record the remainders, which are represented by hexadecimal symbols. Converting 220 base 10 gives DC base 16. To convert any radix to decimal, we use polynomial expansion or the weighted sum method. This involves multiplying each digit by its corresponding base power. For instance, converting 1011.11 base 2 results in 11.75 base 10. The weighted sum method applies to octal to decimal conversion, as shown with 546 base 8 converting to 358 base 10. It also applies to hexadecimal to decimal, like 14A base 16 converting to 330 base 10. The polynomial expansion method can also be used for other radices, such as radix 4. For example, converting 132.21 base 4 to decimal yields 30.625 base 10. To convert octal to binary, replace each octal digit with its 3-bit binary equivalent. For octal to hexadecimal, convert octal to binary, then group the binary bits into 4-bit nibbles and convert to hexadecimal. To convert binary to octal, group the binary bits into 3-bit groups, starting from the radix point, and convert each group to its octal digit. For binary to hexadecimal, group the bits into 4-bit nibbles, converting each group to its hexadecimal digit. Hexadecimal to octal conversion requires 2 steps. First, convert hexadecimal to binary, then binary to octal by grouping in 3s. For hexadecimal to binary, replace each hexadecimal digit with its 4-bit binary equivalent. These are the references used for this video on number systems in digital electronics. Thank you for watching this video on number systems in digital electronics.